So let's solve this problem. We have methane. It is coming in at the reference temperature of 298 Kelvin and reference pressure of 1 atm pressure. It enters a furnace operating at steady state and burns completely with 150% theoretical air. The air enters at an elevated temperature of 390 Kelvin and 1 atm. All right. So let's go ahead and add that information. So we have CH4 at 298 Kelvin and 1 atm. It goes into a furnace where it combusts with air. That air is entering at 390 Kelvin and 1 atm. All right. Now, these are all the reactants, and then the products will go out over here, the products. Let's continue to read. The products of the combustion exit at a temperature of 500 Kelvin and a pressure of 1 atm. And the flow rate of the methane is 2.3 kilograms per minute. So the mass flow rate of CH4, 2.3 kilograms per minute. Kinetic potential energy effects are negligible, and the air can be modeled as our standard 21% oxygen, 79% nitrogen on a molar basis. Determine the dew point temperature of the products in degrees C, and then the rate of heat transfer for a control volume enclosing the reacting gases or the combustion. So this will be our control volume around that furnace. So there's our control volume. And our traditional sign convention is that you have a Q dot coming in, and we're going to find that the answer is negative 1,780 kilowatts for Q dot. All right. Let's go ahead and first get a balanced reaction equation for 100% theoretical air. Then we'll modify that to get 150% theoretical air. So let's go ahead and start. We'll have methane, CH4, coming in, and we're going to bring in oxygen with the air. So that's 3.76 nitrogen. That's the way we are doing it, setting it up. If you look at this ratio, 3.76, that is equal to 79%, 0.79 divided by 0.21. Okay, so for every kilomole of oxygen I need to bring in 3.76 kilomoles of nitrogen. Okay. Then we're going to combust. Now all the carbon in the fuel goes to carbon dioxide in the products. All of the hydrogen in the fuel will go to H2O in the products. There'll be no unburned because it's completely, it says it in the problem statement, there is a complete combustion. Where does it say? It burns completely right here with 150% theoretical air. Okay. So then what we're going to get is a bunch of nitrogen. I'm going to put a 3.76 stoichiometric coefficient in front of that nitrogen. And now what we're going to do is we're going to balance the carbon first. We see that there's one carbon here. Hence, the stoichiometric coefficient in front of the CO2 to balance the carbon has to be 1. All right. Then we balance the hydrogen. We have 4 in the fuel right here. Hence, the stoichiometric coefficient in front of the water vapor going out is 2. Now, I go slow. I add up the oxygen. How many oxygens do I have from the carbon dioxide? 2. How many oxygens do I have from the water vapor? 2. I add them up. I need 4 oxygens coming in to balance the oxygen. So I look over here and I say, what's the stoichiometric coefficient in front of here? It'll be 2. 2 O2s gives me 4 O's. Okay, and I should have put a plus sign right here. All right, so now the carbon's balanced, the hydrogen's balanced, the oxygen's balanced. Just finish out and balance the nitrogen, and so we can just put right here a number 2 times that. And we are now balanced. Now that's the balanced reaction equation with 100% error. Let's now modify it. We'll write a brand new equation for 150% error. Don't change the coefficient in front of the fuel. We leave that as 1, stoichiometric coefficient, CH4. And we're still going to have 2 O2 plus 3.76 N2. We're not changing the amount of carbon, hence we're stuck with 1 CO2 in the products. We don't change the number of hydrogen, so we still have 2 H2O, but we have some unused oxygen as well as some nitrogen like this. So I need to rebalance the oxygen and the nitrogen. Well, because it's 150% error, this is 1.5 times how much air was brought in. So that's the coefficient that we put right there. It's 1.5. If they would have said 200% error, I'd have put a 2 there. Okay. Then I come over here and I think, okay, well, that means that 4 of the O's are used, but how many, if you kind of do the math here, what is this? 3 O2, so I got 6 O's. Hence, I still have 1 O2 going out in the products. Okay, so that's, how did we get this coefficient 1 in front of the O2? Balance the oxygen. And then the balance of nitrogen, it's just 1.5 times the N2. If I want to clean it up, and a lot of times I like to clean it up, I just rewrite this CH4 plus, I'm going to put 3 O2s, and then how many N2s? 11.28 N2s go to 1 CO2 plus 2 H2Os plus 1 O2 plus 11.28 N2s. I should get rid of this little arrow here, a little confusing. There you go. So again, this is a 1 right in front of that O2. So there's our balanced reaction equation. We need that. Now what do? Well, you go back to an energy balance for this control volume. In general, that energy balance can be written this way. The Q dot going into the control volume divided by the molar flow rate of the fuel coming into the reaction combustion chamber minus the W dot going out. Oh, do we have any W dot coming out? No. So we're going to strike that and make that equal to 0, but let's go ahead and write it first. Is equal to the sum over all of the products of the stoichiometric coefficient of each of the products that's exiting times the enthalpy of each of the products that are exiting. And the way we get that enthalpy is it's the combination of the enthalpy of formation of that exiting product plus the change in the molar enthalpy. So let me just do this. I'm going to write it like this. The molar enthalpy of the temperature exiting of that product minus the molar enthalpy for the reference temperature, 298 Kelvin. That's our reference temperature for that product. And we have to sum over each of those exiting products. Now, I didn't leave enough room, so I've got to come down and write the next one for the sum over all the reactants. The stoichiometric coefficient of each incoming reactant times, very similar here, we want that enthalpy of each incoming reactant, and it's going to be based on an enthalpy of formation of that incoming reactant plus the molar enthalpy at the incoming temperature minus the molar enthalpy at the reference 298. Okay, I mean, I could have put T ref there, but I just put T 298 because that's a reference temperature. So we don't have any shaft in or out of power, so that's 0. And we're looking for this Q dot over N dot F. oops, before I start into part B, I already started into part B, we should have finished part A. Let's go ahead and finish part A. If I want the dew point temperature of the products, I first calculate the mole fraction of the water vapor in the products. Well, if I look at all of the products, I have 2 moles of, or kilomoles, either way, of water vapor, and then I have 1 of the CO2, 2 of the vapor, 1 of the oxygen, and 11.28 of the nitrogen. So that's a total number of products in moles or kilomoles going out. So this mole fraction comes out to be right at 13%, 0.9. There you go, a little over 13%. So we take and get the partial pressure of the vapor leaving by taking the mole fraction of the vapor times the total gas pressure exiting. That's equal to 1 atm. All right. So if it's 1 atm, it's 1.032 bar. Hence, you calculate this to be in bar 0.1326 bar. So now I know the partial pressure of the water vapor. What I need to do is I need to calculate the saturation temperature for water with a saturation pressure of 0.1326 bar. So I should have put the units on there, bar, B-A-R. And we calculate that to be 51.3. That requires interpolation in our textbook. If you're using table A2, I encourage you to do that. We've done these interpolations a number of times. But if you take and do the same thing in table A3, because you're interpolating between 2 datum points, you don't get exactly the same answer. You get 50.5 degrees C. So which is it? Is it 51.3 or 50.5? Well, this date is a little closer to one of the datum points in the table, so I'd pick that as the recommended. So our temperature dew point is 51.3 degrees C. But again, if a student submitted their answer at 50.5, I would recognize, oh, they interpolated in table A3 instead of table A2, and I would calculate it, and I would accept it as equally correct. Okay, so there you go. That's our answer to part A. Now, we already started on part B requiring energy balance, and we're at this point. Well, what I want to do is I probably need to go to a clean page to finish out this problem. So let me do that. Let me move to a clean page. I'm going to go ahead and copy this. Okay, so we move to a clean page, and we want to calculate this Q dot for the furnace. All right, so given our balanced reaction equation, we can expand for each of these products. So what are some of the products? Well, let's do it for carbon dioxide. Let's also do it for the product H2O. Let's also do it for the product oxygen, and then let's do it also for the product nitrogen. So these will all be plus, 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 plus. And sometimes I'll add a little P to emphasize this is for the product, this is for the product, this is for the product, this is for the product. And then I have to do a subtraction. So these are all plus, plus, plus. I have to subtract for each of the reactants. Okay, well, what are my reactants? I have CH4 is a reactant coming in, and then I also have O2 as a reactant. That's why I like to put a P, O2P, and O2 reactant, because I have oxygen on both sides. And then likewise I have a minus, and then I have the nitrogen and the reactants. Again, that's why I put a P and an R. This is N2. P and an R, so I try to distinguish these two. Okay, look at the coefficient. We have the stoichiometric coefficient. Well, for the CO2, it was a stoichiometric coefficient of 1. For the water, it was a stoichiometric coefficient of 2. For the oxygen in the products, it was a stoichiometric coefficient of 1. And for the nitrogen in the products, it was stoichiometric coefficient 11.28. Now let's go to our reactants. Our balanced reaction equation had 1 kilomole stoichiometric coefficient, whatever you want to call it, in front of the fuel. For the oxygen, we had a stoichiometric coefficient of 3 in front of the O2. And then we had 11.28. Notice that the nitrogen didn't react with anything, so the stoichiometric coefficient in is equal to the stoichiometric coefficient out. But the oxygen did, and those two stoichiometric coefficients are different. All right, so now we're going to have to put the enthalpy of formation for each of these components, and then we're going to have to put the molar enthalpy at the exiting temperature for each of these components, and the molar enthalpy at the reference temperature for each of these components. Let's first do the so each of these parentheses have 1, 2, 3 terms, just like this right here. 1, 2, 3 terms. Let's get the enthalpies of formation first. So for the carbon dioxide going out in the products, this is not a function of temperature. We just get it from a table. In our textbook, we're getting it from table A25. We want the enthalpy of formation, molar enthalpy of formation. It's all at our reference temperature and reference pressure. And so the first one was carbon dioxide, CO2. And so we need this negative 393,520. So if I want to do that, I'm going to put negative 393,520. And I can see I'm going to be really fighting for space here. But that's just the way it is sometimes. Let me try this. I'll move it over. Negative 393,520. All right. How about for the water? This is going out as water vapor. So we look down and we say, okay, here it is, water going out as vapor. And there's our enthalpy of formation, negative 241,820. Negative 241,820. All right, let's get the enthalpy of formation of oxygen going out in our products. Well, oxygen has an enthalpy of formation. It's one of the building blocks in which people said, well, we're going to set that arbitrarily for our datum point for energy measurements to 0. So that's 0 for the oxygen and also 0 for the nitrogen. So let's go back here. For this oxygen, it's 0 both for the product as well as the reactant. And the nitrogen is 0 for the product as well as the reactants. How about for the methane? Well, we have to look down here. There's a gap in our table, so I cut and paste. And this is methane, and it has an enthalpy of formation. Notice it's gaseous. Negative 74,850. Negative 74,850. All right. Now, let's try to focus on the second component and the third component. So what is the molar enthalpy of the CO2 exiting, and each of those temperatures of the products exiting? The temperature exiting was 500 Kelvin in our problem. Okay. So we need to go and find that molar enthalpy. It's in a different table. In our textbook, it's in table A23. And so they have the molar enthalpy, the molar internal energy, the molar entropy at low pressure. Don't worry about all those, just focus on the first column. So they have it for carbon dioxide. Notice that they put the same information. They repeated the enthalpy of formation, which was in the previous table here. So that's nice, that negative 393,520 kilojoules per kilomole. And we look down until we find our exit temperature. And our exit temperature is 500 Kelvin, so we need this value, 17,678. So it's plus 17,678. Where did that value come from? Table A23 at a temperature of 500 Kelvin, 17,678. The next value is at the reference. Tref is 298, so we need this 9364 minus 9364, and I wish I would have left more room, but I didn't, but I just filled in these two values right here. The molar enthalpy at the exiting 500 Kelvin minus the molar enthalpy at the reference of 298. That's for carbon dioxide. We need to do the same thing for water vapor right here in our products. So it's going to be plus a value. Let's go here. We have to find water vapor column. Notice our molar enthalpy of formation is repeated. Good. We come down. We need it at 500 Kelvin. And then we subtract at 298 Kelvin. So 16,828 is a value that we need for the molar enthalpy. And then 9,904. All right, let's go ahead and write those in here. So it's 16,828 minus 9,904. Okay, now how about the oxygen? Well, what is the oxygen's O2 molar enthalpy at 500 going out? 14,770. Subtract from it the molar enthalpy at 298, 8,628. All right, so let's go put those values in. We have a value of 14770 minus 8682. How about for the oxygen? Well, same thing, not the oxygen, nitrogen. We go to the nitrogen. We get it at 500 Kelvin, subtract off the value at 298 Kelvin. Let's put those values in. 14581 subtract 8669. So we finished the sum over all the products. Now we focus on the reactants. The first reactant, don't forget the fuel. And then you say, well, what was the temperature of this incoming reactant? If you look back at the problem, and almost all of the problems have the fuel entering at standard reference temperature and pressure. So you really don't have a value for this change. It's plus 0 for the fuel because it's coming in at the reference condition. All right, how about the oxygen? Well, it's coming in at slightly elevated temperature. This inlet temperature, we go back to the problem statement, I will, but it's 390 Kelvin, just so that you are forced to use a lot of, looking up values in the tables. Let's go back right here, 390 Kelvin. If it would have come in at 298, then it would be a lot easier. There would be plus 0 over here, but it's not. So we have to look up the value at 390 and then subtract the value at 298. Well, we already know the value at 298 for the oxygen. 8, whoops, this is bad looking 8. Try that again. Minus 8682. We just have to look up the value at 390. So let's look up the value at 390. Well, I cut and paste. So here's a line of temperature of 390. We need that oxygen, so we need this value, 11,409. So plus 11,409, then you subtract 8682. Same for the nitrogen. we know we're going to subtract 8669, but what is its molar enthalpy at 390? So for the nitrogen at 390, it's 11,347 plus 11,347, then subtract. There you go. Okay. Is that it? That's all. At this point, you jump on your calculator and you run the numbers at least 2 times to make sure that you can calculate it quickly, and you get Q dot divided by N dot of the fuel equal to some value. I calculated negative 745,761 kilojoules per kilomole of the fuel, the methane that's coming into the reaction chamber. Well, what was our mass flow rate of the fuel methane coming in? It was given to be 2.3 kilograms, not kilomole, of the fuel per second. I do a little extra subscript on this so that I'm not messing these up. It's what kilogram are we talking about? Well, we're talking about the kilogram of the fuel. Let's go back to our problem statement and just verify this mass flow rate of the fuel. So let's get rid of this number. The flow rate of the methane fuel coming in is 2.3 kilograms per minute. So I need to divide by 60 seconds. All right, and you can calculate a mass flow rate of 0.03833 kilograms of the methane fuel coming in per second. Well, we get the molar mass of the fuel for methane, 16.04 kilograms per kilomole, and that allows us to calculate the molar flow rate of the fuel. So the molar flow rate of the fuel is 0.00239, probably more digits, but that's where I stopped, and they're in my calculator, in kilomoles of the fuel per second coming in. So now we come up and calculate just what is Q dot. It's going to be Q dot divided by N dot of the fuel, which we just calculated, times the mass flow rate, or the molar flow rate of the fuel. And we calculate Q dot negative 1780 kilowatts. That's the answer to part B. So in summary, a lot of looking up of the enthalpy of formation in table A25, the enthalpy of formation for the fuel, for each of the products, each of the reactants, and then the molar enthalpies, H bars, these molar enthalpies, the molar enthalpy right here in units of kilojoules per kilomole. The units are given in the header of the table. And then we have a product of carbon dioxide, we have a product of water vapor, and the oxygen is both in the reactants as well as the products, and the nitrogen is in the reactants as well as the products. So there you go, and that's our answer for part B, and that agrees with the value here. Well, hope that was helpful.